Hello, this is Parisa. This is assignment 6, optimization and stochastic gradient descent or SGD. Um, in the last video, we discussed CNNs and we discussed that we're using Atom for optimization, but I didn't go through the details of what optimization actually means. So here we are going to talk about that. And the beginning, as usual, import some packages, random, numpy, matplotlib, pyplot. And from scalar.model selection, we are importing train test split. Um, and then the random seed is set to 42. I'm not sure why 42 has been chosen, but random seed. Um, so I don't want to go into the details, but it makes your random number to be the same every time you run it. That can be helpful for making sure that like every time you get the same result, but it's still random. So it's hard for me to explain it in a very short time. And here we want to generate some data points out of nowhere. So we just generate a random set of data that are integer values between 40 and 120, if I'm not mistaken. Um, oh, I didn't run the first block, I think. Oh, it's still running. Okay. So that should show me. So it should be integer values between 40 up to 120, I believe. Yes, a low and high, and 100 shows the number of random points in there, and then they are sorted. And then we convert this NP as array item divided by 30. So height. So I'm a little bit confused because it says 50 random weights, but I think it meant 100. Anyway, and height in foods of target values we want to assign. So this is like weight of some people between 40, between. So it should be from 40. Maybe they changed the values later to 120. And we're generating some height values random for random people that we're converting it to food. Maybe that's why random randoms. So it's an integer value added. So it's generating different weights regarding the different heights regarding the weights of the person. So it's like a random number plus something between 2 and 3, and then plus an item divided by 30. So that makes sense. The item is different weights in this list. So it's kind of random, but also related to the weights. And then we want to have a function to plot data with an option to plot a line. We'll see in the future. It's called plot data line. It takes x and y and the model as input, and then don't worry about this part now. And it defines a figure, and it's just want to make sure if you don't pass the model to it, it just draws a simple line. Based on is if it's not none. If it's none, it just plots a line. If it's not none, if there is a model in there, it wants to plot something related to that model. We want to see later what M and C would be in the model. So we don't know it yet. And then plot something on top of that. So here, because we don't have a model as an example, we're plotting data line for the x and y we defined up there. So these are like, this is like a scatter plot, heights versus weights. And then we use train test split to split those random values to train and test by choosing 90% for training and 10% for testing, and we are giving it the random state, which is the random seed we defined up there. It was better to say seed maybe. And here you can see how they're correlated, like the correlation is kind of linear. So the model has two parameters, m and c, and is expressed by y equals to mx plus c. So it's how they are related that we defined here. So mx plus c is the how this model has been defined. So it's the relationship between height and weight, and now we can see what m and c was up there. And so we talked about a loss function last time. So here the loss function is mean square error, is the mean of error between the desired output and the current output squared. So let me make sure I forgot to run anything on the way, and then split, and then here is where we want to discuss. So we want to write a code to calculate the mean squared error. So the error is the prediction minus the target, which is our expected value, and the squared, we need to square it, and then we want to calculate the mean, which we can use the np.mean function from numpy and return the mean squared error value. I run this, and then we want to so here the predicted model is this. This is repeated, and then x is the feature vector. So to update, we want to update the weight parameters. The parameters m and bias c in each iteration of stochastic gradient descent, which is one of the so this is different than Adam that we discussed in the previous section, but it's also another optimization algorithm that uses gradients to decrease to make the mean square error get closer to zero. So that's why it's called descent. So it want to decrease it and decrease the gradients of them. It's like you can tell that the maximum or minimum of a function is its gradient. It's where its gradient is zero. So that's why we want to decrease the gradient of it. And we need to calculate the gradient of the MSE with respect to M and C. The gradients are defined this way. So the gradient is like taking the derivative of this function, which results in this one here. And so it's according to gradient according to M, and then according to C. There are two different values for gradient. This is basically because m is multiple of x, but c is a constant value, so c doesn't show itself in here. And n is the batch size that we discussed in the previous one. The update rule for weight and bias is given by, so we want to update it, whatever m is, it's we need to decrease it or subtract this value, the gradient, from it. But this eta is a learning rate, like stating that don't decrease directly the entire value. Maybe we need more adjustments. So give it a learning rate ranging from 0 to 1. so that it decreases, not instantly but gradually. And then, did I run this? Yes. Exercise 2. If we want to finish another task, we write the code to implement the parameter update rule. So we want to implement this parameter update rule. We need to define stochastic gradient descent in the first place. It takes the input and output, and then M and C, and the learning rate, and the batch size. So how it works, and this is so we have the data, but we want to load batches in small batches. So we need to select a random batch or a limited number. So that's given by batch size. We select n or different data randomly from the data set that we had. So it's a random integer between, so in this as like a random integer between 0 and the shape of image. I didn't expect this. Yeah, in the size of batch size, I just saw this. So it's a range of different random indices. And then squeezing it gets rid of extra dimensions that don't have any values. Like if it's 28 by 28 by 1, like the previous example, it makes it 28 by 28 because that third dimension uh, doesn't do actually anything. It just adds one dimension. This is basically to better better use of memory. And that, so we know that the y is equal to x dots. So it can be a matrix. It's a matrix actually. X is a matrix. So we need to do a dot function. Use a dot function here defined and the formula dot x, where is it, plus c. And we define the error by this difference of the prediction value and the actual value that has been loaded from y of those indices, random indices given um, from the random function. And then, so remember we calculate the gradients of the loss with respect to the parameter. Calculate the gradient for the batch. So this is the function of the gradient 2 divided by batch size. So in here is our batch size. And then we want to apply this, that we have the error. So the first one would be error times x, or dot x, I think. Yes. So x dot error actually. And for c, we don't have any c because c was a constant. It goes away in the gradient. But this one stays the same. 2 divided by batch size times the error dot sum. So dot sum makes this summation in here. So this one also needs to be summed. Yeah, so the dot function does the summation itself. And the next thing is to update. So updating, we want to take m and make it equal to m minus eta. So we have learning rate as input down here, and eta times this gradient that we just calculated. So m new is equal to m minus learning rate times gradient m, and also the same for c. And at the end we return m and new m and the new c. Let's run this and run this. So we define a model with m and c. And do we want to write the parameters? M and C here. So this is the model, and this is the initial values. Like the model should be the orange line in the initial. So this is how it works. Um, we pass x and y to it and the model. That its values has been defined randomly. So we want the model line to fit on the actual relationship between height and weight. That's how that lines and the plot function up there was saying that if the model was given, draw a line for the model. And here we define the learning rate a very small value, so it keeps updating gradually, step by step, with very small value. The batch size is given as 16, like how many data items to look at once, and then the number of iterations. So we want to do that gradient descent algorithm on this model for 10 times to see how it progresses. Does it reach the, can it fit or not? And to do so, we go for the number of iterations and we apply the stochastic gradient descent optimization on the training x and y, giving the defined m and c that come from model that are initially random values. And the learning rates and batch size are also defined up here. The prediction would be x passing the x tests to this formula. So x test dot m plus c would be our prediction each time. And the loss would be applying the loss function that we defined up there by giving it the prediction and the y-test. So the differences between prediction and expected value. And then we want to print how this loss changes. We also can plot it. I think we are doing it later. So let's run this. So it says in the first iteration, there is a big loss. As you can see, there is a big loss. And then as it goes by, it gets smaller and smaller, meaning that it's actually learning. So in the next section, we want to see how to plot the loss to see how it changes. So it just plots as losses, and these are more about the labels and titles. And we want to plot this, and we see how it decreases along the time for each iteration down here. And then we also want to plot the line and see how the final values are changing. So we could, I would have liked to do this. Because I really cannot just keep not playing with values. This is just in my nature. So we defined a new model based on each M and C, and we want a plot line of it on the new model, and then see how it affects. Still be showing a lot of plots, but you can see how the progress is happening in the beginning. So these are new random values, I guess. And then, yes, this is the first iteration. So it suddenly jumps from up there to down here. And the next iteration, it goes up again. So that's why we need to choose a very small learning rate for this process, because it keeps fluctuating at the beginning. And then it goes down again, but closer, but not close enough. And then tries to adjust itself, and then adjusts. So it partially adjusted the center, but now it needs to play more with adjusting M and C to make this make the alignment correctly. This is the final value, so it's not perfect, but it's something. And this is the final, yeah. So it should be the exact same with this one, if we can see it. So have a good one. Oh, and I promised you to show the result for the previous one here. Um, we want to plot the score value. So the test accuracy for one of the samples is 99%. Is absolutely high value, and you can see that the score evaluation score is going up from zero to one, and the accuracy is cannot go above one, like it's reaching the perfect value. um, and here we can save them all. And when we save it, and we also plot the results, and also show the test accuracy of and round it for the first value, we can see that it's loading in the right way. So it's the same plot as this one. So it's loading, saving it and loading it. Where does it save it? Here on Google Colab, and you can see the saved files, a5cnn.h5. Okay, take care and bye.